lecture on how to control what the optimizing the control. And now
you're ready for practice. Give you a better example.
and today she's going to talk about the transport of information.
Yes. Thanks. Okay, so my voice has not improved, of course, in just one night, but I'll try to still go through this lecture often, and I made it shorter so that hopefully I can make it through all of it. So what I want to talk today is one thing that hybrid systems are really good at, which is to convey information from between different systems and sort of transfer information. And of course, when I talk about information, I have in mind quantum information, although one could also think about just transferring classical information. So what I will do is to sort of show some examples in which we can, on how we can achieve this transfer of information, but I think that they will be covered much more in detail by other speakers in the middle school, so I will not focus too much on them, just give you the ideas. And then I will focus a bit more again on this particular system of hybrid spin system, and again show how we can achieve this transfer of information by using spins. So, I already started. Why do we want to sort of transfer information between distant quantum registers? So the idea is actually quite old. I think that one of the first mentioned that I could find is by Grover back in 1997, and as usual, Grover doesn't publish his articles, so you can find them on PH only, in which he first mentioned how to do quantum telecomputation or computing at a distance as a way of doing computation in an efficient way. And the idea is quite simple, and it has been, I think that one of the most famous paper about this idea of doing computation in a distributed way is the paper by Kimball, which is called the Quantum Internet, just because it's a very cool name. And this is a picture taken from this article. And so the idea is to have some quantum node where you might have a few qubits that can make some local quantum algorithm, for example, entanglement amplification or quantum error correction, and you can use them as some local memory. But then, of course, if you want to scale up your system, you would like also to connect them one to the other. And why would you try to use this modular architecture or distributed architecture instead of having just a computer which is all interconnected in a very dense way? I think that there are two different types of benefits. From one side, if you take the point of view of the experiment, if you really want to have a system in which you have all your qubits close to each other so they can talk to each other at the same time, it becomes very quickly difficult to implement experimentally because you still need to have access to each one of the qubits to control them. And if you have a very dense architecture, it becomes more and more difficult. For example, if you think in terms of bringing control lines to each one of the nodes, then it becomes a tangle of wires. So having something which allows you to sort of have distributed units might be beneficial. You can focus, of course, have very good control on these separate units, and then try to implement some transfer of information in a way which is also robust and maybe requires less control on the wires themselves. Also, there's been a lot of work on the theory side of this distributed quantum computing, and people have come up with very efficient ways of implementing quantum computation on distributed architecture, which also, again, give you some benefit in terms of the resources that you need for the implementation itself. So there are some possible benefits of this architecture, and so the idea is, well, the question, if you want, is how do we actually manage to connect these distributed registers? So what are possible ways that we can try to implement in order to connect these? And as I say, the one possibility was, for example, proposed by Jeff Kimball back in 2008, which was to use, if you wanted, the most natural carrier of information, which are photons. But of course, this is not the only possible way of connecting different quantum registers, and there have been many different proposals for connection between the electrons. Photons are very good if the quantum nodes are separated by large distances, but if you instead you're just trying to separate them by little bits so that you can bring the control lines, maybe the solid-state architecture becomes more beneficial. So you have still a compact quantum architecture, but not too dense. So possible ways of achieving this information transfer, as I said, here are just some examples. It's not meant to be exhaustive. But we have so-called flying qubits or photons. So this is really the idea, which is also, if you want to take it in order to achieve quantum communication protocols, in which now you have, the goal is not longer to do quantum computation, but just to transfer information over long distances. Then photons are, of course, the carrier of choice, but maybe you still need some solid-state or atomic systems in order to really reach these very long distances. When you use this solid-state or atomic system as quantum repeaters in order to avoid too much losses of photon and information over long distances. You can, of course, flip around the schemes and also use it. The quantum repeaters now become your unit of computation, and then you have this distributed architecture. Different ways of coupling distant unit of quantum information can be given by collective degrees of freedom. For example, motional degrees of freedom, which are collected among many trapped ions, can be used to transfer and couple distant ions. We can consider transmission lines also some sort of collective degrees of freedom and use these to connect more isolated qubits. It's been mentioned yesterday that mechanical oscillator can also be used as quantum transducer to connect distant qubits. So this is another possible example. And then finally, we can also use spins and the intrinsic coupling among them in order to transfer information. One possible example, again, nuclear or electronic spins. So as I say, I don't want to really present all details of all these possible modalities, but I think that other speakers will actually sort of talk about this. Yes? No? Speaker. Some of you will talk about some of this? Yes? Good. Okay. So that was my guess. But I wanted to at least give, I think, one slide for each modality to just give you a flavor of what are possible techniques that one can use. So the first one for photons, the idea, again, this is a picture taken from the Gilmore paper. The idea can be quite simple. So we can create a coupling between photons and, for example, an atom inside a cavity, and then use control to then transfer this information encoded now in the photon into another cavity where that information is mapped onto a second atom. So the idea is very, very simple, and it's based on the cavity quantum electrodynamics, of course, techniques using Hamiltonian. And if you want the theoretical protocol which underlies this type of technique is, of course, just teleportation. So what you would like to do is not really to implement, if you want, the teleportation algorithm, but the goal is instead to achieve gate teleportation, which is slightly different. But of course, gate teleportation builds upon the teleportation algorithm itself. So for the teleportation, what we have is that you have two parties, Alice and Bob. So this will be your two distant quantum register, which want to exchange some quantum information. And so the idea is that they have some shared entangled pair, which is an initial resources among them. And then Alice can prepare some initial state, which is some unknown initial state, at least unknown to Bob. And she would like to transfer that state to Bob. But of course, you cannot measure the state and then transfer it. because you cannot, with just a single copy, you cannot really measure completely the state without destroying the convey the quantum information. Also, you cannot copy the state because there is the so-called cloning theorem, which tells you that you cannot ever copy an unknown quantum state. So there is no really way to sort of for Alice to look at its state and then say, okay, well, here was my state, now I reproduce it. There needs to be some slightly different algorithm. And so what it's done is that Alice can perform a particular measurement, which is a Bell state measurement between her state and a part of this entangled pair. And then she can transfer the classical information, which she obtained about this Bell state measurement, to Bob. And then Bob will perform some operation based on the result of Alice's measurements on a fresh on its part of the entangled pair, and as a result, it will obtain the state which Alice had at the beginning. So this is the basic of the teleportation algorithm, and you can also write it down in terms of a quantum circuit. So it is very similar to what I showed before. So what you have here is these are the two parties of a Bell state shared by Alice and Bob. This is the state that Alice has at the beginning. And then what Alice does is with Bell state measurement. So this is accomplished by a CNOT gate and Hadamard gate here. It's a controlled NOT operation, controlled by the input state onto the part of the Bell pair. And then just a Hadamard, which basically would create a superposition on the initial pure state. And then she measure two qubits here. Based on the measurement result, here we operate some other controlled NOT operation on Bob qubit or a controlled strings operation. And as a result of this, we can get out the same state that Alice had at the beginning. So let's say this is just a teleportation algorithm, which is not really what one wants to do in terms if one is interested in achieving this distributed quantum computation. What you really would like to do is also the ability, in some sense, to operate the gates at a distance, gates between distant qubits. So a very similar algorithm can be used in order to also teleport a quantum gate or an operation among distant qubits. One can very simply just modify the algorithm and introduce the desired gate that one wants to operate. There are better schemes than this. This is just the illustrative of what you can do. But by just modifying in a very simple way the quantum teleportation algorithm, one can achieve that the output of the algorithm itself is no longer the initial state that Alice had, but is the modified state, which basically implements the gate onto the distance qubit that Alice had at the beginning. So these two algorithms, like the teleportation and in particular the gate teleportation algorithm, are really the basis of how to achieve this distributed quantum computation in larger architecture, in distributed architecture. So one can sort of build upon these basic tools and achieve a very efficient quantum computation in a distributed way. So how can one implement this type of algorithm? So one of the first implementation of this gate teleportation had been done back in 2010, but this was done in some sense it is like an implementation of the gate teleportation, but it's not really what we want. Because in this case, the gate teleportation was also applied on photons themselves. So what we would like is instead to use photons to teleport gates onto mapped qubits, at least in the spirit of this industry, which is for hybrid systems. So this was not really hybrid. It was still a very nice experiment. So they were using 6 entangled photons, or 6 photons in this interferometer, in order to achieve a CNOT gate among two distant photons, or also a control phase operation, two different implementations. What people have also realized is, of course, entanglement swapping, which is, if you want, this fundamental operation, which is a first step toward this gate teleportation among distant matter qubits. So one of the first implementations where we trapped ions by Randall Blatt and the Weiland groups back in 2004. And of course, because I work on MB Center, I just will advertise MB Center results. So there has been several groups working on achieving entanglement between photon emitted by the MB Center and the MB Center spin itself. And also there has been a recent result in which, just because the picture is nice, and also other groups that have been working with, this is a picture from Donaldson group in Delft. They achieved entanglement between two MB centers, which were in two different MBs in two different cryostats. Basically, the idea is an optical table, so this is why we have this 3 meter distance. And what we did was to force create entanglement between each individual MB center and the photon. And then by combining the two photons and achieving entanglement swapping between the two emitted photons, we can now map out an entanglement between the two schemes here. So as in all of these schemes, these rely, of course, on the measurement of two photons in the correct ports of your detector, so that if you want the heralded schemes, and so typically the rate at which you can create this entanglement pair is not very high, but they managed to have very good fidelity in the local operation, so that the rate was not too bad. I don't remember exactly actually how it goes, but
it's like one successful entanglement per 25 minutes or something like that.
But the 25 million, it was relatively fast. So I mean, yeah, graduate students were not unhappy to try to repeat it from the two ends of the campus. So which means, and hopefully we will have soon a result. I don't remember how many, some kilometer apart, 1 kilometer apart between two parts. Hopefully this will happen soon. Okay, so this is for photons, and of course photons are very nice carrier of quantum information. You can go larger distances. But if you want a more compact quantum architecture, maybe that's not the best way of achieving this. They're good for quantum repeaters, but if you want just a quantum computer, maybe there are better ways of doing this. So here are some different possible modalities. So one is to use so-called quantum bus to, again, transfer information between distant qubits. So this is an idea which goes back, I think, to around 2004 in the group Roshovkov. And the idea is to use a transmission line, here open up in order to show that diagram, in a way which sort of replicates the physics that one really finds in cavity QED. So here you have, if you want a circuit QED scheme, in which you have, if you want, this cavity with mirror here, which are given by this gap in order to contain, in this case, it's no longer an optical photons, but it's a microwave photon. And then you have a Cooper pair, which is your qubit, to which you can couple now with the electromagnetic wave. So it's, if you want, the physics is very similar to cavity QED, but now you can realize it in a very compact way. So if this is, of course, the cartoon picture, but then you can really go down and do it in practice in the lab. And as you can say, you can have a very compact circuits in which you can possibly scale up and try to scale up the system to many qubits connected to many quantum buses. And hopefully somebody will talk about it. You did already, so that's about what to say because you have the experts here. So it's been mentioned yesterday, and I'm sure that it will be mentioned again, that one can also use a mechanical system to try to connect distant qubits. And so I just picked one example, which is, I found it was particularly interesting. This is from Peter Rado. in which the idea was to use, again, some mechanical oscillator to couple to a spin qubit. So what you have is a mechanical oscillator with a magnet, so that depending on the distance, you have more or less coupling to a spin qubit, and you can resonantly couple to the oscillation of the qubit itself. But when the twist on this scheme, which has sort of been implemented and studied by different groups, what we were thinking of doing was to put some charges on top of your mechanical oscillator itself. So now it becomes, if you want, an electro-mechanical oscillator. And so if you have, for example, two of these oscillators which are nearby, depending on the state of the two spin, you have different possible configuration of the oscillator themselves. And this also will sort of change the charge which is associated with the oscillator itself. And because you are using this charge, then you can just use some lines to bring an electric field, and you can then control the state of the oscillator by these external lines, and in turn this allows you to transfer information between your spin qubits. And the nice thing is that this is, if you want, it's just a linear architecture, but you can think of just arranging your oscillator in particular ways, and in particular, you don't need really to arrange the oscillator. What you need to do is to arrange the electric line which controls the oscillator, and in this way you can create different type of architectures. So for example, you could create an architecture like the one here, but you could also, in which basically your qubit will be just coupled linearly in a linear chain. But you could also sort of rearrange the electric coupling so that the qubits are effectively coupled in a sort of like star type of oscillator. And depending on which configuration, geometric configuration you implement, there are different types of if you want, tasks that can be achieved in a more efficient way. So if you want to transfer information from one node to the other, maybe linear architecture is what you want to do. If you want to have one controlling qubit at the center, as we were discussing yesterday, some kind of actuator which control other registers, then this type of star configuration might be an interesting one. So I don't know if anybody is really working on this, because it's a nice concept, but it seems particularly complicated. But I think that it can be hopefully put in practice. Okay, so as I say, these were just examples which I hope that you will get more information from other people. But the last example I want to sort of focus a bit more on, because probably you will not hear from other speakers, so I just want to give you a bit more detail on this. So the fourth modality which I want to present to you in order to transfer information among distributed quantum registers is to use spin chains, so just spin which are in a linear geometry, or maybe even more complex geometry, which can transfer information among different quantum registers. Here again spins, but we could also think to couple to different types of qubits. So how can we really achieve this transfer of information? Well, the idea is that because you have this space, they're close enough to each other that they actually interact with each other. And of course, then you could tell me, well, why don't you use them as qubits? Again, we go back to the idea that maybe they're too close to each other, so I cannot really control them individually. And so I can hope to use them as quantum wire, but not as quantum register themselves. So how do we achieve this transfer of information? One way is the following. So let's say that I have an excitation on the first qubit, then the qubit spin will interact with its neighbor, and so we just flip-flop with the other. So the excitation, which is initially in the first qubit, is transferred to the second one, and then little by little will transfer down the whole chain. So what type of interaction can achieve this flip-flop among the spins? Well, we can use this type of Hamiltonian. Actually, this one is the wrong one. which I first had the correct one and then the second one is So what is the Hamiltonian which actually does this type of interaction? Let's see if somebody can suggest it.
Just change the plus and minus on I plus 1.
Perfect. So let's say that I have sigma I, and then I have sigma I plus, and sigma I plus 1 minus plus permission. Okay, so this, of course, preserve the Zeeman energy if you want, or the magnetization of your string of qubits, and just have operate this flip-flop between nearest neighbor of the space of themselves. So why did I put down actually this Hamiltonian? So what will turn out in a few slides is that you can actually use this other Hamiltonian if instead of having a chain of spins which are initially all polarized in one direction, if instead your initial state is given by the maximally mixed state. Okay, so for this type of Hamiltonian, for this type of initial state, this Hamiltonian, it's called flip-flop Hamiltonian, and or XY Hamiltonian, and this other type of Hamiltonian, they are completely liquid. So, depending on the initial state, then you can use this type of Hamiltonian, but unfortunately, what you would usually have, if you have just a chain of spins, is neither of these two Hamiltonians. This is not the typical Hamiltonian that you would have. What you usually have is instead another type of Hamiltonian, which is the so-called dipolar Hamiltonian. And here I wrote it down in a slightly weird way, just because it sort of highlights different parts of the Hamiltonian which I actually care about. So the dipolar Hamiltonian is just going to be given, if you want, by the typical dipole-dipole interaction among two different magnetic dipoles. And then we only preserve the part of this Hamiltonian which commutes with the total magnetization. Because typically total magnetization is the largest energy in your system, and so we only want that part of the Hamiltonian. So from this would be like, if you want something like that. J, we will only consider the part of the Hamiltonian which commutes with the magnetization, which can be written in several different ways, for example, something like 3. Yes.
There are markers.
Oh, which may work. Yes. Thanks. That's perfect. So this is the only part of the Hamiltonian that we actually care about, because this will commute with the total magnetization, which is the main energy. So I can rewrite this in this particular way. And why do I care to rewrite it in this particular way? Well, because this part here is actually equivalent to this double quantum Hamiltonian. Okay. So in this way, I sort of try to show to you that actually my dipolar Hamiltonian already contains this Hamiltonian which I can use for transport. And so then it's up to me to try to extract only this part and disregard the other one.
So you might have already said, but what is BIJ?
So this is just like the strength of the coupling among two strings, having the same effects. Yeah, so typically, like this is depend on the distance and the relative position with respect to the external magnetic field, for example. So if I have only this Hamiltonian, what happens? Well, I have basically no transport. I have some evolution. My spins do have some flip-flop because this Hamiltonian also contains some part of this flip-flop Hamiltonian. But because of this other relational space, because of also the part which is proportional to the ZZ term, I also have some phases during evolution, and this sort of block my, sort of stop my diffusion. I'm not sure. This froze, it's not so bad. You do have a bit more evolution than this. But basically, you never really reach the other element chain. So what I'm plotting here. So again, the idea is that I have some initial state with one this polarization is transferred to spin L here in this axis as a function of time, and with if L is equal to N, it will give me the fidelity of the transfer from one end to the other end of the chain. So as I said, this natural internal Hamiltonian doesn't really give you transfer. So what you would like to do is to try to engineer the Hamiltonian that you actually would like to use in order to achieve the transfer. And so what happens, as I said, is that with the polar Hamiltonian already contained this Hamiltonian that you can use for transfer, plus another part which you would like to erase. So how do you try to erase this part? So what we can use is just a simple technique which allows you to engineer the Hamiltonian. Okay. And the idea is that I can represent my typical the polar Hamiltonian as this vector along the z direction, because, as I said, this is the Hamiltonian which really commutes with your magnetization in the z direction. What I can then do is just to rotate my system, and so rotate also the Hamiltonian along the x direction. Okay, by just applying some pi virtue poles along the y direction, I effectively rotate what my interaction does. So now I represent it as this arrow along the x direction. So the polar Hamiltonian along the x direction turns out to be given by the double quantum Hamiltonian plus minus this term which I would like to erase. So if I alternate between these two axes many, many times and quickly, and I can do it, for example, with a sequence like this, on average, what I have is the sum of the two possible Hamiltonians. So on average, what I get is just this Hamiltonian, which is the one which I want. Of course, I need to select my timing in the correct way, because this Hamiltonian is only h prime, and this one is plus 2 prime. Okay. So this is a technique which, of course, works here, but you can think to use it much more generally. Anytime that you want to engineer some Hamiltonian, some natural Hamiltonian, in order to simulate or create a different Hamiltonian. Of course, what I've done here is basically the following evolution. Okay. Purple doesn't, you cannot see it, but then it cannot get erased. So what I've done is basically to have a total evolution, which is just something like the evolution under the typical Hamiltonian along the z direction, and then evolution under x, and then evolution under z, and then etc. So I alternate. So the fact that I'm saying that this one is almost equal as if I had e to the minus I, the sum of the Hamiltonian along the z direction, plus Hamiltonian in the x direction, etc., with the corresponding time, is only an approximation. So what I can do is to concoct some more complex pulse sequences, which will give this approximation instead to just the first order, also to higher orders. And this particular sequence, for example, cancel out the two more orders of approximations. And in principle, one can work hard and try to make it so that it cancel out even higher order of corrections. Typically, that's not really needed for a typical application. You start seeing many more other errors before you see these higher order corrections. For example, post error entering play much sooner than higher order correction. But what you can do is then engineer this transport Hamiltonian, or more generally any other Hamiltonian that you might want. Of course, there are limitations in what you can do, and this is one of the reasons why I'm trying to generate this double quantum Hamiltonian and not this flip-flop Hamiltonian here, which I just erased. I do not try to engineer this flip-flop Hamiltonian, plus sigma minus, just because this one is not contained into your initial natural Hamiltonian. So depending on the symmetries of the problem, you might or not might be able to engineer the Hamiltonian that you want. So what happens if I use that particular Hamiltonian which is good for transfer? Well, let's say that I initially all my couplings which are equal. So I can assume that all my spins are at equal distance one from the other, so the coupling which depends on the distance will just be equal to each other. Then I do get some transfer. Here, see that some transfer which is being achieved down to the last spin, but it's not perfect. So I never achieve it here. I go back to the full fidelity equal to 1, which would be a telltale that I have achieved a perfect transfer. So the problem is that even if I have this ballistic type of transport, which is different from what the dynamics that I had for the initial lateral Hamiltonian, the transfer is still dispersive. So I lose some of my polarization onto neighboring spins. So one strategy to overcome this is to use some particular type of couplings among the spins, which have a particular shape, with square root of j n minus j, where j is the position of the spin itself, and n is the length of the chain. And if I do that, then now I do have perfect transfer. So you can see that here, I hope I go up to 1. So I really have a packet, if you want, a spin wave which bounces back and forward in my chain, and it stays very much, so it doesn't get dispersed, so it's of course spread out on neighboring spin, but then it sort of comes back at each way.
Is that because Bj goes to 0 at 0 and n? Because it doesn't go to full on any other j, right?
It doesn't go to
Full height. Fidelity doesn't go.
Oh, yeah, so I mean, you achieve this particular coupling will give you perfect transfer for the n of your chain, which is what you have. So it is, it's, if you want, it's a geometric constraint, so you could be able to engineer different coupling which will give you perfect transfer at, say, speed 10 of 100 or something like that.
So how much is that dependent on the boundary condition that you have? Because in a real setup, you will have the last spin will couple to many other things also.
So
This is now a perfect one-dimensional system
Yes.
with perfect boundary conditions.
yes, yes. I mean, I don't know if that's been ever really estimated. So in principle, like the idea is that you could always use control to decouple to whatever is out there. I think, I mean, I hear your concern, but I'm much more concerned about creating this couple.
Oh, yeah, no.
So I never given like a very hard look at that problem because there seems to be something which is even worse.
Yeah.
So, yeah. So this couple are nice. It's a nice geometrical construct, and people have found this theoretical solution, which is similar to having like a larger spin n with an equal sort of try to go from plus n to minus n, you would have the same type of condition. But I do not think that it's really very much realistic. So we need to try to find some other ways of really achieving this, this perfect transfer, which is not achieving this perfect sort of engineering decoupling. So in principle, one could think of sort of engineering the position of the spins in order to achieve this. If you have this other type of architecture in which you are engineering the architecture itself, with transducer, one could think of achieving something like that. Another way is to use this type of techniques of Hamiltonian engineering to achieve this effective coupling on a dynamic base. So there are ways of trying to do this, but it's not sweet. So another problem is to try to initialize the quantum wires. So why do we use these spins in our system as quantum bus or quantum wire instead of a qubit? Most probably it's because we don't have very good control on that. So here, in order to achieve this Hamiltonian, I was only using collective control. And that seems to be sort of okay. I will just blast my whole system with some microwave. I don't care about controlling individual spins, but I should still be able to hopefully control them all together. But in the same way as I can only have some partial control on my system, it's also going to be very difficult to initialize them. So one could think of like lowering the temperature, go to a zero temperature in which all the spin will be polarized in one direction. But as I was saying yesterday, maybe that could work for electronic spin, although you will still have maybe some errors. If you try to use nuclear spin, it's going to be even more difficult. So in general, it's going to be quite difficult to really achieve this initialization. So to solve that problem, the question is, can we achieve transport even if we have no control on the initialization of the spin wire? So one way, so there are ways in which you can do it without any initialization at all. A second way is to say, well, it's probably difficult to achieve zero temperature, but it's much more easy to achieve almost infinite temperature. So you don't really need to achieve a perfect infinite temperature to be describing your system already as just this maximal mixed state. So this is an initial state which is much more forgiving if you want, and it's quite easy to achieve by experiment. So can we then, if we use this initial state, can we achieve perfect transfer? What do you think?
Well, you're asking a question. So the answer must be yes.
Yeah, so there is, I asked the question so I could drink my coffee. Yes. So there are some good news. So if I just use this mixed state chain, I can of course transfer one bit of information. Okay. So let's say that I prepare everything in this completely mixed state, and then I just say that my first spin, so everything is mixed state, identity, and then I prepare my first spin, let's say in zero state, this polarized state, and then I can transfer this information into my last spin here. At the end of the day, this will become zero. And I can also transfer a state which is 1. Okay. So what I can do is just say, well, I will encode the information in this sign of my polarization, and then I can transfer back. However, if I want to also transfer some state which is more interesting, let's say the superposition of this, then this transfer using the same type of Hamiltonian doesn't really happen. So the problem is that although I can transfer this separate state, we acquire an extra phase, which depends on the characteristic of the Hamiltonian, the length of the chain, and so on and so forth. So I can transfer this basic state, but the combination will acquire some phase, which is up here below. So you might calculate what is the phase that you expect and do some correction. But if you do not want to do that, what you can do is a nice trick, which is to encode the information into two qubits. So as I said, like you cannot really transfer this type of state, which would be basically this state here written just in intensity matrix form, because you acquire this extra phase, which depends if you are in the zero manifold excitation or in the forced excitation.
Is that because the transport is happening in the z basis, and that's why the phases?
Yes,
Okay.
but you could think of engineering Hamiltonian which transfer the x excitation, but then you can
And you have
transfer
the same
the z,
problem.
so you still have the same problem. So what can you do? Are you asking this question?
Do you assume that this is a fluctuating state, fluctuating zero temperature state, initializing?
I assume that I have almost infinite temperature.
It's not fluctuating. Then you can measure once the phase and then use that. Like
Yeah, so as I said, you
you
could like measure your phase, but then you should in the end apply a different correction for each individual.
Back and forth.
Yes, but you should always like apply probably a different phase depending on what is your initial state. And so that sort of contradicts the fact that you do not really know what state you want to transfer.
Because if you transport the photon polarization through the fibers, and if you transport it through the fiber that is telecom fiber lying down
Yeah.
somewhere, you have the same problem.
Yes.
So that's what all these mechanisms that Niklas is
Yeah,
saying.
you can correct. So
Correct.
that's one step.
If it's stable, that's what I said. If it's fluctuating on the time of the transport, then it's
No, you can think of it as a state. But there is also a different ways of doing things in this case. Maybe we floating too. Maybe this is the second way.
Do we have to have a maximally mixed transport chain?
No, but let's say that. Yes. So the problem, as I said, is that you have a phase which depends on how many excitation you have in your system. So if you fix the number of excitation, then you always have the same type of phase. So how do you fix the same number of excitation? Well, as I say here, you have either 0 or 1, so they're different. But now you can always think of using an encoded state in which you use 2 qubits, which have always the same type of number of excitation, and they can still represent being qubit 0 or 1. So for example, you can your 0 state to, let's say, 0, 1, and your 1 state to 1, 0. Now these 2 states have the same number of excitations, and so we will acquire always the same state. So any combination of them, representing any possible state, will always acquire the same type of phase. So then, without doing any correction, you always know what is the phase which is transported. It's always the same, so we don't really care about it. It becomes, again, a collective phase which can be factored out. So what we can do then is to transfer, if you want, with logical basis. Okay, so it's for operators, again, if we are talking about mixed states, we always need to talk in terms of density operators. And so all of these states can be transported, and this is for this particular engineered coupling. At a particular time, they all achieve perfect transfer. Here is the correlation between my initial state on spin 1, and then spin 1 and 2, and the final state on spin n and n minus 1. So by using this very simple encoding, so just like a 2-qubit encoding, you can transfer any state using this totally mixed state. And you can even use, for example, 4 qubits to transfer an entangled state to physical qubits encoded in 4 logical qubits encoded in 4 physical qubits, and achieve perfect transfer of entanglement in a completely mixed channel. So without needing to do any further correction steps, which is a different strategy. Okay, so this is, if you want some of the ideas about how to implement information transfer, I think almost running out of time, so I want to talk a little bit about possible implementations. So the first type of implementation which we have actually been working on in my lab is to try to simulate these ideas using nuclear magnetic resonance. And this has some advantages. The one which is really important is that we can use these natural crystals, and then the position of the spin are very well determined. So we know what is our initial Hamiltonian, and we can really have good control of what is the dynamics of the system. Of course, there is problems that as every time you implement a resonance, you need large ensembles in order to detect some sizable signal, and so we don't really we are not really able to measure a single spin, and not even to control individual spin. So the system that we use, just very quickly, is a particular crystal of which is called fluorapatite, and the typical crystal looks like this. So as a matter of fact, I use diamonds for the rest of my research, which do not look like gem, but this particular crystal I bought on eBay, and it was supposed to be a pendant. So another time for my research, I do use jewelry for it was $10 or something like that. But still, it was sold as a pendant. When we chop it off, of course, I put this. So why do I have chains here? So this is like the basic lattice structure. It's basically an hexagonal structure where these red spheres are fluorine 19, spin 1 alpha. And if you put many of these basic cells on top of each other, what you start seeing emerging are these chains of spins, which are very close by to each other, while the distance here is much larger. This is coupled to the fact that, of course, the coupling strength goes as the distance cubed. And so what we have is that the coupling inside the chain is around 40 times larger than a coupling to another chain. So for the type of dynamics and times that we use, typically what we see is really a behavior which mimics very nicely the 1D behavior that we have. And the type of tools that we have is to generate the transport interaction using these Hamiltonian engineering techniques that I show. And also, we worked on preparing the initial state and measuring out the final state of my transport protocol, taking into account that I don't really have individual control of spins. So it becomes a bit difficult to say, okay, I'm measuring only the spin at the end of the chain. So the chain are of course interrupted by defect in the lattice. We don't really know what they are, but I can see other substitutional spins. But what we see is that you can sort of identify that you have finite length chains, and you can address, although without full control, but you can have some small addressability of the spin at the end of the chain. So then what we do is sort of to do this transport protocol, and what we really wanted to do was to sort of compare a protocol in which we do not do anything to initialize our system, and we do not try to measure the spin at the end of the chain, with the case in which we do initialize, the spin at the end of the chain, and we do measure only the spin at the end of the chain. And so this is not what we want, but it's a control protocol, and this is what we want. And then we have intermediate type of experiment in which we do only the initialization, but not the readout step, or we only do the readout step and not the initialization. And by symmetry, we should give you basically the same type of result. So again, this is to make sure that our readout initialization protocol, which is the most challenging steps in this type of system, are actually working out. And of course, in order to have this transport Hamiltonian, we apply this sequence of poses in order to engineer the Hamiltonian that you want to achieve. So what we get is that we can find very nice transport-like behavior here. So the dashed line are the analytical solution to the problem. If you consider only nearest neighbor coupling, you can solve it perfectly analytically. And what we see is that we see the transport out of the, if you want, one end of the chain. Unfortunately, we do not see the transfer back to the other end of the chain. For two reasons, the chain were too long in these experiments, but also you have a distribution of chain lengths. So even if you get a crystal with a lot of defects, you will still have a lot of different chain lengths. And then the time at which you have the revival will depend on the chain lengths inside. So we are working on sort of circumventing that problem, but for the moment I don't have the result for that. The other thing that we did was to also create and transport this logical state. In this case it was sigma y, just for example. And again, we can find a very good match between our theoretical prediction and the experiment. So as I say, this is nice in terms of what we can do for the control of the interaction themselves. But there is a lot of problems because it's difficult to measure the spin at the beginning and the end of the chain. So another implementation that we would like to work on more is using nitrogen spin chains, where the spins at the end of the chain are now NV centers. So in this case, we can really address, initialize, and detect the NV center at the end of the chain. But when you try to create an NV center spin, you will always have to implant some nitrogen. And then there is some conversion probability from nitrogen to NV spin. And you will always have it, even if you have a nice picture of this with dry spots in particular location, what you cannot see is that in between them you will have some dark spin, which are these extra nitrogen that you have implanted. This is bad on one side, but on the other side you can use them to connect the NV center, which might be too far away from each other.
How linear does it have to be? So does this break down if you have more of a 3D arrangement with the dark spins?
Thank you for your question. I will continue onto that particular subject. Yeah, so one of the reasons why we are using for the moment this other neutral-spin crystal is that the implantation is not precise enough. And so what we really have done is on the theory side to sort of study how you can achieve this transfer of more complex 3D networks, or how robust is your transfer process to errors in the chain itself. And it's work that we have done in my group, but there is actually a large community studying this type of problems. So I think that I probably have like 5 minutes, so I just try to give you one strategy on how we can achieve perfect state transfer. As I say, that you can do this engineer on the coupling, very difficult. You can try to do some active control, which is quite promising. So you can try to add some control in your spin system in order to either mimic this engineered coupling or achieve some different protocols and different Hamiltonian which still allow the perfect transfer. So even if you implanted your spins in precise position, that still doesn't give you perfect transfer. They will have equal coupling, which does not achieve perfect transfer. It achieves perfect transfer for 3 spins, which for me is not a chain. And a lot of people have published works in which you go like a state transfer, and then you look at it and it's like 3 spins. So a third strategy is to achieve this so-called weak coupling regime that's been proposed independently by many different groups. So the idea is the following. So let's say that I forget about the fact that I have a nice spin chase. Now I have something which is completely random spins. I still have, let's say, like 2 empty centers and would like to connect them through these networks of other spins. In this case, let's say P1 single nitrogen defect. I can rewrite this geometric picture in a slightly different way using a network representation with the adjacency matrix of the coupling, representing the coupling. So here I still have the 2 spins which I want to connect, and then this various line correspond to the coupling among the spins. I sort of arrange them in sort of random order. And so what you see is that the more sort of like thicker lines represent a stronger coupling, and the smaller, like thinner line represent a weaker coupling.
So you assume that this is a random network.
This is
not
a
and not a scale-free network.
Yeah.
Like the old sense.
Yeah. So what you can do then is to try to ask the question, can I still achieve perfect transfer between these 2 distant modes inside this very random network? And it seems sort of impossible. Yeah, I agree with you. It seems sort of, okay, why would we even try? So it turns out that actually you can try to achieve something which is not bad if you do the following trick. So what you want to do is to connect very weakly your initial and final spin of your network, or your target and source and target of your network, to the rest of the network. And the idea is that now you sort of pump in some information very weakly inside this complex network. When the information sort of bounces around with very fast dynamics, and then very slowly will try to trickle out on the other end of the network. And because you have this very different time scale, the time scale of which these 2 spins are connected to the rest of the network, and the complex dynamics inside here, you can do, there are many different ways of thinking about it. One way, you can do sort of an adiabatic approximation to the system, in which you're sort of neglecting completely the internal dynamics here, and now this becomes just like a large complex single spin to which you're coupling your 2 different spins here. So irrespective of what are the details of the dynamics inside here, you can still try to achieve perfect transfer between these different couplings. So what it turns out is that you're effectively trying to connect your 2 spins to a collective back mode of all the other spins here. So if you have a chain, a linear chain, even with some disorder in the coupling, this you can do in a very efficient way. You can have a resonant coupling between the 2 spins at the end of the chain and the collective mode of all the network. And this allows for quite fast transport, which is now quite robust. So it is fast, although of course it's limited by how weakly you need to couple the spin, so that the spin are only coupled to this collective mode and not all the other modes in this.
So these are collective modes, they don't couple to each other.
So yeah, so like you have the internal Hamiltonian of all your network,
Yeah.
and you can write down what are the energy
Like
modes,
eigenmode of that.
the eigenmode of the network.
So the many body eigenmodes, or are these?
Yeah. So you
Not-
will, so you
not
will have like
quasi-particle eigenmodes.
not.
Not quasi-particle eigenmodes. You can make an approximate theory of these couplings. And
Yeah.
then you can also get something like this, which is quasi-particle. Something that's equivalent to quasi-particle. And that would also
Yeah,
be,
that's
they
a
interact,
way
you
of
get
that's a
something
way
like
of
modes.
looking at it. Yeah. So like you will have like many different modes here, many different energy levels, and then what you want to do is to connect your spins to only this particular ground state mode. And if this coupling is weak enough with respect to this energy gap, then you will never populate this higher level here. And you can do that in a resonant way if you have a linear chain. If you have a more complex network, as we were considering, where you need to do some extra tricks, some control on your spin at the end of the chain, which is sort of okay, but should be able to control. And so by adding this extra control step, then you can take not only a linear chain, but also some random network, and still be able to achieve quite good transport. Of course, you pay something in terms of the speed at which the transport itself can happen. And we did some simulation, and so you can get some sort of transport time in terms of how far away the spins are. So this line is the transport time when you apply this extra control step, so it's slower, but it achieves a quite good fidelity. This line is when you do not apply any control. It looks much faster, but the fidelity of transfer was around 20%, so it's not good. So, of course, in this result, although we were considering a complex system, it was still quasi-1D, so you had spins which were sort of randomly distributed, but it was sort of around a semi-linear geometry, otherwise the transfer speed becomes very risky.
So, can you say anything about the boundary conditions in the network? Does the network have to be finite? And also...
So, I mean, the network could be in principle infinite, but then the speed of transfer becomes infinite.
Yeah,
Time of
okay,
transfer becomes infinite.
so you want
So,
the network
like,
to be...
the problem is that, like, the larger the network, the
Yeah.
smaller this gap becomes.
Yeah.
So then the coupling has to become even weaker,
Yeah.
then it becomes longer and longer.
And do you need to know what's the minimum amount of information that you need to know about the network?
So you don't really need to, in principle, you don't really need to know what is the exact geometry of the system. What you can do is to sort of try to implement like a sequence like this, and then at some point you will hit the resonance condition, and then you're all set. So you don't need to sort of identify all the possible positions, but you need to know at least what is this lowest mode here.
So,
And you can do the trial and error if you want. Okay, so I think that with my time. So what I sort of taught to you in this lecture, first lecture was some strategies on how to control these hybrid systems. And instead today I talked a bit more about how to connect different hybrid systems. And then sort of give you a gallery of possible modalities which other people will sort of expand on. And then I focus a bit more on this idea of using spin wires to connect distant other qubits or spin qubits or other kinds of qubits. And in particular, I focus on two different techniques. One is this Hamiltonian engineering, which you can sort of achieve the Hamiltonian that you want to use for your transport. For example, the double quantum or the flip-flop Hamiltonian, starting from a natural Hamiltonian, which is what nature gives you, and only use a very minimal set of control, which is just collective control over all your spin. And then I talked a little bit more about how to achieve perfect transfer in different systems. And one way that one can achieve that is by using this weak coupling regime and this resonant condition in order to get transfer of information, even if you have a very complex network in which you do not really know all the possible interactions. Thank you.
Questions? Paola?
So just on the like the last decoupling thing, is that equivalent to the quantum zero effect?
That's another way of looking at it. Yeah. So I think that there are many different ways in which you can try to understand it and look at it. So one is this, like, for me the most intuitive pinball stuff.
What is that?
Pinball.
The game pinball. Oh, I've never played it.
Yeah, the game pinball. So like you just put inside here some information, just bounce around, but there's only one way of escaping. And so, well, at some point you will achieve this perfect transfer. But yes, so zero effect is another way. So
But in people, there's a gradient, right?
well, in pinball, the wall is hard. So I guess my point is if you're trying to do the state transfer, is the state hard? Can it be shared among many of those spins as a function of time? And so
Yeah.
your calculations show that eventually it
Yeah.
collapses onto the other spin.
Yeah.
But my issue with the pinballs, it's like a quantum pinball. Because
It is
has
a quantum.
to
It is a
follow
quantum.
all
Yeah,
the
yeah. So
paths.
I mean, like what you have is a quantum walk in this complex network, and then you can achieve that. And it's, I mean,
It's a fun.
Yeah, yeah.
yeah. And the fact that so like in the quantum pinball will happen even if you're not in this resonant condition, but it will still be bad at fidelity and very weak. When you add this resonant condition, now it's really a quantum pinball because you're really going and attracting this collective mode. So quantum Zen is another way of looking at it. You sort of basically because this is very weak, then you can again erase the internal dynamics and you sort of just slowly achieve transfer to the others.
Well, but while your pinball is bouncing around in the network, is it gonna lose phase and state and like decohere?
I mean, in principle, no, because all the interactions are just unitary coherent interaction. Then, of course, you always have decoherence on top of it, which is something that I have not presented we also consider. But yeah, in principle, like what I consider just coherent interactions.
I was just thinking that if you were using the dipolar interaction, it seemed as if for the earlier part of the analysis, it was only the nearest neighbor interactions that mattered. And now you have a complex network.
So, okay. The fact that you have only nearest neighbor is, of course, an approximation. So, if you have only a nearest neighbor, then you can analyze nicely your system, you can find this analytical solution, this ideal coupling, and so on and so forth. But it's not what you have in practice. And that's one of the things why achieving something which is more robust in terms of, for example, this recoupling is quite nice, because now you can consider also this extra coupling. So in some sense, if you have a linear geometry, if you consider all possible coupling, effectively you will have an efficiency matrix which looks more like this. So even if you have a 1D geometry, you have an effective 3D type of structure, and so you really need to use these type of things if you want to achieve random transfer.
So the dipolar interaction is strong enough that you have such kind of.
So in a linear chain, like the next nearest neighbor is 1/8 of the nearest neighbor. So for example, in the experiment that we see, you can fit very nicely our experimental core to the analytical model, which only considers the nearest neighbor coupling. So it's not too bad, but we also do not go for very long times. So when you start going for longer times, you start seeing the fact that you don't have a 1D system, you have many chains, so that you have the other coupling and so on and so forth. So it's a good enough approximation, but it's not perfect. So if you really are sort of trying to get a perfect state transfer, you need to consider also these other couplings.
So do you know what the coupling strengths are between the nodes?
I mean, like here I'm just saying, okay, I just geometrically put some spin in a lattice, and then the couplings are just like magnetic dipole couplings among two different spins, and that's sort of sets the interaction strength, so I can a priori calculate if I knew what the position are. So for the simulation, I can do that. In practice, you will not know what's happening, exactly happening, but you do not need to know.
Yeah, so that's just a little useful bit of procedures for the AMO experiment. So you have this like this distribution of spin chains, and then where do you create the expectations of what it is you have to do?
Yeah, so basically I have almost an infinite ensemble of parallel chains, and then these chains are interrupted by defects. And I do not know exactly what these defects are. So there are some protons substituted in the place of the fluorine. There are some vacancy missing, some nearby under-intrusion or something. What it turns out is that they sort of shifted the resonance frequency of the spin, so basically they do not look like anymore as fluoride lentille. So then what we say is, okay, I have some finite chain. Now I cannot really address an ensemble of finite chains. I cannot really address the spins at the end of the chain, but they have slightly different dynamics because they have only one strongly coupled spin and not the other one. So using that, I can engineer a differential dynamics between the spin at the end of the chain and all the other spins. And in that way, I can leave some residual polarization on my spin at the end of the chain, while all the other spin now will become in this maximally mixed state. And that's my initialization step. Then once I have that, I have something which looks like, as usually I list it, but basically the initial state of 0 is identically with epsilon sigma z on the fourth spin. Let's say that I'm good and prepare it completely, tensor product identity on all the other spins. The matter is a symmetry, of course, also my last spin will be in some slightly polarized spin. But because I'm average at the end, I can consider it just like this.
So you sort of like select the spins at the end of
Yeah. And then I can also repeat the same trick in order to, so my measurement is of course just a total magnetization of the sample. So I can, again, apply some control sequence so that even if my observable is the sum of all the spin, I can sort of map this to just measuring this four spin at the end of the chain. And so I can sort of have some control in the initialization of it. And so this is what I mean by these small sequences here. So this small sequence is just like two values, of course, with a small time interval between them. Basically, it is all coherence on the spin inside the chain because they evolve fast, but still preserve a little bit of coherence on the spin at the end of the chain because they evolve slowly because they have only one couple. And so they prepare this type of initial state. And similarly, I can do the same type of sequence before measuring everything out. And so I also only see signal coming from the spin at the end of the chain or from all the spin if I don't do it.
I have one small comment and one small question. The idea of this resonant transport, I think in chemistry there are also sort of somewhat similar strategies. If you have a very large public molecule, you want to sort of break it off, you can use these pedestal states, intermediate states, to bring the reaction from one point to another. There's also photosynthesis, although there is not many body, but but the small question you have is, how do you ensure what you buy on eBay is what you're supposed to get?
Well, you just buy some of them, and then some are good and some are not. So I actually bought... No, but I bought... Yeah, well, I mean... So I know...
I just bought something on eBay for the first time.
So I know some places where this crystal come from, so like, typically I buy them... No, not the vendor, but if the vendor tells me, oh, I have a fluorapatite from Durango, Mexico, I'm like, oh, okay, that probably is correct. But like, I bought some other sample, and then I received like a package, and there was like a little sample which I can hopefully use. And then like the guy was like, oh yes, I gifted you also some other crystal, just rocks or that.
They're crystals.
Yeah, they were crystal and some inclusion. I don't need that, but okay, thanks.
So this is a good time to break, and let's take a 5-minute break. First time Paola again.